Well, have you ever been confused by Bayes' theorem in statistics and probabilities? I know I have been confused by it, and welcome to my finance teacher. I hope by the end of this video you'll be much more familiar, much more at ease with probabilities and particularly with Bayes' theorem, as I'm going to try my best to explain the general idea of the theorem using an interesting example. Particularly, we're going to have a look at the ongoing pandemic to learn a little bit about probabilities. Let's make it both useful and interesting. So let's say we have some reality over here, which we will later describe with some probabilities. But let's say the reality is that some people are sick and some people are healthy. And let's say this includes the whole population. And you can't be both sick and healthy at the same time. So these two are, let's say, mutually exclusive. And also it's an exhaustive list of what can happen in reality, where people are either sick or healthy. And next, to introduce some numbers, let's say 5% of the population are sick, meaning that the remaining 95% of the population are healthy. And before we introduce the interesting things about testing, if you just randomly select anyone from the population without any additional information, only using the initial information that we have so far on how many people are sick and how many people are healthy, you'd get a prior probability of a 95% chance of selecting a person who is healthy, or a 5% chance of selecting a person who is sick. So there's the first concept for you of prior probability. Before we go on to the additional information using some COVID-19 tests and how all of that applies to probabilities and Bayes' theorem, let's just rename the event over here a little bit so that if you see the Bayes' theorem formulas anywhere else in the textbook, it'll be a little bit easier to read those formulas. Usually in the textbooks, you'd have an exhaustive list of events, including perhaps A1, A2, A3, or whatever it is. In this case, we're just going to use A1 and A2. A1 denoting sickness, and let's say A2 denoting health. And now that we've made this change, we can throw in this formula as you might see it in a lot of statistics textbooks. The formula for calculating Bayes' theorem. And what does it say is, if you want to calculate the probability of AI, whatever it is, whether you want to calculate the probability of a person being sick, that's A1, or the person being healthy, that's A2. Given some additional information, and we'll introduce that additional information with a test for COVID-19, then this is the formula that you want to use. Hence, let's introduce B with testing, where this B is the test for CV-19, and of course the test result will depend on whether the person is actually sick or healthy. As we see over here, the probability of the test result showing that the person is sick, given that the person is actually sick, is of course going to be quite different from the probability of the test result showing that the person is sick, given that the person is, let's say, healthy, A2. And starting with this first probability, the probability that the test result will say that the person is sick, given that the person is actually sick, is called the sensitivity of the test. And often the sensitivity of the test is not 100%, however worrying that may sound. If we have a look at this Wikipedia study on different types of tests, one of the cheapest tests that you could use is an antigen test, which is actually not as sensitive, not as accurate as some other tests, which are a little bit more time-consuming and perhaps more costly. So this antigen test has sensitivity which ranges anywhere between only 34% to up to around only 88%. Let's be generous over here and give it the higher range of 88%. So the probability that the test will say that the person is sick, let's say B is being sick with CV-19, given that the person is actually sick according to the reality, is 88%. That is the test sensitivity. Now moving on to the second probability, that the test says the person is sick, given that the person is, well, actually healthy. That is called a false positive. And it's actually quite difficult to find the data for the false positives rate on CV-19. But looking at the CDC recommendations, looking at this website from the Food and Drug Administration, that's fda.gov, we'll see that the actual false positives rate depends on the prevalence of the disease in the population. So, for example, if 10% of the population have the disease, with a test that is 98% specific, which is well close to the current tests on CV-19, the rate of false positives is going to be somewhere around 20%. And with a lower prevalence, the false positives rate is only going to increase. In our example, where the 5% of the population is actually sick, the rate of false positive should be relatively high, but let's just be somewhat kind to the tests and give that a 15% chance of a false positive. And with all of this, with the additional tests running, we can now calculate posterior probability. There's another concept for you, which is revised probability of being sick or being healthy with some additional information coming from these tests. In our example, let's actually calculate the probability of being sick, given that the test result shows that the person is sick. So if we want to calculate this probability of being actually sick given the test result showing sickness, in the numerator we're going to have the prior probability of being sick multiplied by the probability of a positive test result given the sickness. And in the denominator we're going to have a couple of things. First, we simply copy the numerator into the denominator and add the product of the prior probability of being healthy multiplied by the probability of test results coming up positive for a healthy person. Let's move the formulas a bit to make some space, and in the numerator I'm going to have 5% multiplied by 88%, whereas in the denominator, first I'm going to copy the numerator and then add the prior probability of being healthy multiplied by the probability of false positive. And all of that gives me a 24% chance that the person is actually sick, given that the test result shows the presence of the disease. So as we see, this probability, posterior probability of 24% chance of carrying the disease has increased with the additional information of the test from the prior probability of only 5% chance. As you see, the probability increased by over 4 times, from 5% to nearly 24%, but it's nowhere near 100% certain that the person is actually sick, given the positive test results for the virus, for the disease. Hence, this emphasizes the importance of additional follow-up tests for those who have a positive test results on these relatively cheaper, relatively faster antigen tests. Next, let's generalize a little bit our understanding of the Bayes theorem to a case of more than 2 outcomes, more than 2 events. Instead of having a sick and healthy population, let's have a look at an example with 3 possibilities, where you are running a company producing some equipment that contains semiconductors, and let's say you have 3 suppliers of your semiconductors. Semiconductors coming from Intel, semiconductors coming from TSMC, Taiwan semiconductor manufacturer, and chips coming from Qualcomm. Let's say Intel supplies 45% of the chips for you, TSMC supplies 30% of the chips, and Qualcomm supplies 25% of the chips. And if the batches of chips have already been mixed, you can't identify them by simply looking at the chips. Any random draw of one chip from a huge batch of mixed chips will show you these prior probabilities of coming from a particular supplier. Next, let's have a look at a test where the test result for the chip is either the chip is defective or it's fine, it's basically functioning. And these three suppliers of chips have different percentages of their chips being faulty, which is, let's say, 3% for Intel, 6% for TSMC, and let's say 4% for Qualcomm. So the probability of the chip being defective, being faulty, given that it comes from one of these suppliers, is shown within this column. Now, similar to our previous example, let's say we have a test result of a defective chip. Let's say we found that, oh well, this chip is actually broken, it's defective, it doesn't work. What are the chances that it's coming from, let's say, TSMC, as it, let's say, supplies the highest rate of faulty chips? In order to generalize the previous formula into an example with 3 or more events that you're looking at, you simply have to add all of those events in the denominator. Basically, the denominator should list all of the possibilities for the test result show that the chip is defective. If the test result is showing that the chip is defective, it could be because it comes from the first supplier, or it could be because the chip comes from the second supplier, or it could be because the chip comes from the third supplier. Similarly, in the previous example, if the test results shows the presence of the virus, it could be either because the person is actually sick, that's probability of B given A1, sickness, or it's because of the false positive, the probability of B given A2, a healthy person. We simply list all of the possibilities for the given test result in the denominator. So what we're going to have in the numerator first is the probability of A2, 0.3, multiplied by the chance of the chip being broken, given that it comes from the second supplier. That's 6% chance. That is what we have in the numerator. We're going to simply copy that into the denominator and add the other two possibilities, where the chip comes from the first supplier, Intel, multiplied by the probability of a faulty chip coming from Intel. And the remaining last possibility is the chip coming from Qualcomm multiplied by the probability of the chip being faulty, given that it does come from this third supplier. And that, of course, will be equal to the ratio of these two numbers, which is just over 43% chance. If the chip is faulty, given that the second supplier has the highest fault rate, any faulty chip, any randomly chosen faulty chip will have nearly 43% chance of actually coming from that second supplier. And that is how you generalize the Bayes theorem formulas from 2 possibilities to 3 and more possibilities. That concludes the video, and good luck on your tests.